10, 9, 8, 7, 6, 5, 4, 3. Okay, okay. All right. So, I would like to try one more. Welcome back. Okay. I would like to. Sorry, I just. Oh my goodness. Yeah, late grading yesterday, calculus exams, and early this morning as well. Yeah. Anyway. Hope you're doing all right. What I would like to do instead of digging into the new section right away is I think it's helpful to take a look at one of those combinatorial proof things from yesterday, just to see another example. I mean, I think they're so strange. Oh, actually, before that, just like, hey, today's Tuesday. Quiz is available today. It's available tomorrow. You pick your day, do that last quiz, last response due tomorrow, last homework's due Thursday. There's a pre-final math as a process assignment. I need to check what the due date is. If the due date's a problem, just somebody email me. I'll extend it. I'm not really all that concerned about exactly the due date of that. It's just like a chance to again look at everything before analyze for yourself before taking the final. I will have daily office hours starting Saturday. May 9th. Hour and a half in the morning, hour and a half early afternoon. If you need to meet at other times, that's fine. That's why I only scheduled an hour and a half here, an hour and a half there. Just send me an email. I'd be happy to meet up one on one at another time. And then the final exam will be available May 15th, 16th, 17th, 18th. That makes 4 days total, so I hope that'll work out okay. And again, it's not meant to be like a very, very, very long exam or anything like that. Okay, so let's look at one of those yesterday style problems, this combinatorial proof thing. So I won't be completely as formal with this. I just want to get a lot of the big ideas out on the table, basically, so that you can fill in the details on your own. So for all n in positive integers, 2 times n, choose 2. Let's write that better. 2n choose 2 is equal to 2 times n choose 2 plus n squared. Now this one's a strange one. Don't get me wrong. This one is really strange. So if you note, this was in yesterday's notes PDF, but it was towards the end. Just remember as big story to prove one of these sorts of statements, and we're not going to do the whole thing, right? This is just going to be an outline of ideas. So like, should a good proof start with a let n be in positive integers? Yeah, sure. Right now, I just want to step back, do big picture stuff. Remember yesterday's big idea with combinatorial proof is you're presented an equation, and the way to prove this equation is true is you come up with one counting question, and then you answer that one counting question twice. You provide two different answers to the counting question. And I don't mean different as in the numbers are actually different. I just mean they look different, right? So like you come up with a counting question. We're going to do that right now. We're going to come up with a counting question and answer that counting question with the final answer being 2n choose 2. And then we're going to revisit that same counting question. And then by thinking about the question differently, we'll come up with another answer which is also accurate, and that answer will be 2 times n choose 2 plus n squared. Right? That's what we need to do. All right. So first of all, let's pick the side that's easier to deal with. In my opinion, I think the left side is kind of easier to come up with a story than the right side. So let's put this out to the crowd. What would what would be a situation of 2n choose 2? What's a 2n choose 2 kind of situation gonna be? Set of cardinality 2 times n to start with, yeah, and want to choose two things from that set, right? So there's 2 times n things total. And yeah, we got to choose two of them. It doesn't matter which two, as long as you don't select the same two things twice, but like all the ways you could possibly do that. So I'm going to suggest we do the following, just for funsies, right? Like it's actually much more fun and makes things a bit more accessible to not always phrase things in set language all the time. I mean, you can, but for this one, just for fun, I would like to phrase this in terms of a Lego piece. So imagine you have a Lego, You know those like super thin Lego pieces that still have dots on them? Like there's two dots in one direction, and then you like there's these versions that just two dots, two rows and two columns, but then there's like the two rows, four columns, or the two rows, six columns, or this kind of. I don't know how many, so that's what this sort of dot dot dot. You know what I mean? These little Lego pieces, and I want to imagine there's two rows, and then there's n columns here. So you take a Sharpie, right? And you are allowed to take among these dots that are all showing here, any of these dots, you are allowed to take a Sharpie and color in two of the dots, right? So you've got this Lego piece, Lego piece with two rows and n columns. So how many dots total? 2 times n, right? That's where the set of cardinality 2n is coming from here. And then we're going to Sharpie in two of the dots. Sharpie in your choice of any two dots. Of any two dots. The number of different ways to do this? The number of ways to do this is, there's 2n dots total, and you choose two of them. So that's the left side. Okay, so just sort of a quick answer to this question is what provides the left side. What about an argument that's going to come up with the text on the right side over here? So 2 times quantity n choose 2 plus n squared. Well, I want to think of this 2 times n choose 2 a little differently. So first of all, just as a bit of scratch work, let's just write the expression we're given different. So instead of 2 times n choose 2, how about n choose 2 plus n choose 2, right? Because if you had n choose 2 and n choose 2, you could collect like terms as we use the language to get 2 times n choose 2. And then as well, so I'm going to copy this plus sign right here is that plus sign. I'm going to write n squared differently. I'm just going to write it as n times n. Now here's the thing. N choose 2 should be a situation of there's n things and you can choose two, and you have to choose two of them. You choose exactly two of them. So we're looking for somewhere in the problem we could have n things and you choose two of them. Well, where are there n things? I mean, my eyes already just drawn to the first row. So to me, I see this n choose 2 as Sharpie in two dots from the first row. You have to choose from the first row. Sharpie. Let's actually, since I'm pointing to a number here, let's write it this way: the number of ways to Sharpie two dots from the first row. Right? So the two dots must be chosen from the first row. Well, and then let's take a look here. There's another n choose 2. How about that's the number of ways to Sharpie two dots from the bottom row. So these n dots here, choose two of those. But look at the way we worded this originally. You had this Lego piece that had two rows and n columns, and the way that this word problem, that this counting question was worded here, I didn't even write down the entire question, but like here the process was you can Sharpie in your choice of any two dots. And how many ways are there to do this is, I guess, the counting question. But take a look at what's underlined in blue. Down here, underlined in blue, is picking two dots from the first row. Underlined in red is picking two dots from the second row. So we need to talk about this one. So thoughts? Let's have a discussion. Ow. Anyone care to share? Choosing one dot from each row, right? That's like the missing. See, when over here it was just choose any two dots, and there was no restriction on whether the two dots come from the first row or from the second row or one from each row. And so the way that the right side is working out, we're taking the situations and kind of partitioning them, cutting them up into like three situations of either the first two dots, not first two dots. We're only choosing two dots. Either the two dots come from the first row, or the two dots come from the second row, or as was just mentioned, one dot from each row. Right. So this right here is choosing one dot from each row. Right. Each row there's only two rows, so there's an n and an n, and here the product rule applies. Right. So this, I mean, I know it's a lot of things to think about here, but like if it's just choosing any one of the n dots from the first row, and then any one of the n dots from the second row, and you have to do both procedures, that's a product rule situation. So I hope that works. Again, there's like this is very much in an outline form. There's not a lot of words written here. I think I did a lot of hand waving, but this is kind of one of these where, of course, you could if you need to if the conversation here, like if the setup is somewhat clear, then you can put words to this stuff. But I just wanted to sort of point and draw pictures and just kind of provide another sort of argument through this. Are we okay with this, or are there questions? I think if you want my opinion about this chapter 6 on counting, the first three sections take a little getting used to, but then, once you're through like the product and sum rules and then the combinations and permutations and counting via bijections, it's all kind of okay. This section we looked at yesterday about combinatorial proof it's kind of more challenging because you got to come up with the counting question and then answer it twice. It's like hard enough sometimes to answer it once, yet alone come up with a creative way to rethink about and answering the question without thinking about the way you already answered the question. I think that's what makes yesterday's thing a little challenging. Um, Today we'll look at section 6.5. It's the last section of chapter 5. Section 5 in chapter 6 is the last section in the counting chapter. It is also the last true lecture day. So there's so much I wanted to cover, but once the semester ends and grades are in, I want to write up a couple things and hand them out as completely optional reading, that kind of thing. And you can of course ask questions over the summer if you're curious about some extra things that we didn't get around to. Right? But what I want to do tomorrow then and the next day, and I haven't organized it yet, but I want to just review some problems. Like I want to tonight come up with new review problems, some that are more kind of challenging and like chance to review equivalence relations and functions and this kind of thing. Okay, so that's the plan for tomorrow and Thursday. I haven't even written anything up yet, so that's why I haven't uploaded any notes. But I'll do that tonight. Today we actually end on a really rather nice topic overall. Now you'll see some kind of odd applications of it today, but conceptually it's not bad, and the kind of questions I would expect you to answer in a final, I'm not picking anything. I don't want to pick anything hard here. So you'll see amongst the practice questions that I post online. So conceptually today's topic is way nicer than yesterday's. Okay, pigeonhole principle. So this sounds super funny, but the way it's usually worded is something like this. If k plus 1 or more pigeons fly into k pigeonholes, those pigeonholes are usually thought of as like cubbies for some reason. Cubby holes, boxes. So you have k plus 1 or more pigeons. Every pigeon needs to choose one of the cubby holes. There's k of them and fly into the cubby hole. Every pigeon ends up at its destination in one of the boxes, in one of the cubby holes, in one of the pigeonholes. Now this sounds so silly and obvious, and we don't prove it. We just take this as a principle. So we take this kind of obvious idea. Then there is at least one box By box, I mean the same as pigeonhole, right? There's at least one box containing two or more pigeons. That says two more pigeons in the notes. I'll say it differently here. Containing multiple pigeons. That's really it. So it's just the pigeonhole principle. I just thought of it actually today to clarify what this is. Like we've seen so many really challenging proof techniques. What is this about? The pigeonhole principle is just about like providing a proof using this kind of very obvious idea of there's more of this than that, or there's less of that than this. That's all that's going on with the pigeonhole principle. So I actually pulled up the Wikipedia page, and literally, you see here this picture provided of pigeonhole principle. You'll see there are 9 pigeonholes or boxes. There's actually in the upper left box here. I don't know if it's visible very much, but there's 2 pigeons in there, right? So if there's 10 pigeons and 9 places they can be destined, then 2 pigeons have to end up in the 2 or more pigeons have to end up in the same hole, right? So there's got to be a pigeonhole that has multiple pigeons. There could be even more than one. Like in this example, there's only one hole that has multiple pigeons, but if you had 30 pigeons and 9 holes, then you could have several holes have multiple pigeons. So it's really conceptually not meant to be much. Like everything else we look at in this chapter, I think, is much harder. So just as a brief example, let's say you have like a conference. There's like an academic conference. There's a check-in procedure, and 27 people appear at the same time to check in. 27 people appear to check in. Now, there's probably no conference out there that would do it this way, but check-in is by last initial. Like, and just, I mean very literally by last initial. Like, there's a line for the people whose last name starts with Q. Nobody does it that way, right? Like, usually several letters are clumped together. But let's just say that there's 26 separate lines. Then at least, right, 26 because of the 26 letters. I'm just trying to provide a very starting first example of this. Then the whole point is that at least one volunteer who's taking care of one of the lines has to check in multiple people. Okay, another brief example. Say you have possible scores on an exam. Are integers from 0 to 100. So let's say there's a large lecture class. A large lecture class has 300 students. Is that like a large lecture class at UWL? I mean, obviously we're not meeting in person, right? But like Psych 100, is that like 300 people? I took, well, at my institution, I took history, I think it was History 1A was what it was called. And that was in Wheeler Auditorium, which seats 900 students. So I took history. Actually, I didn't take the class. I sat in it for funsies. But so I did actually take other classes in Wheeler Auditorium, like astronomy 10. Anyway, 300 doesn't seem too large to me. Okay, sorry. All right. So here's the thing. If 300 students are taking a test and test scores range between 0 and 100 and only integer scores, no like 70.5 is not going to be allowed, just to otherwise we won't be able to count what's going on here. So then the point is, and there must be students who are in the same score. And you didn't need 300 students for this to happen, right? This would have happened with 102 students as well. So if a class had 102 students and scores were integers between 0 and 100, with 102 students, you would have this guarantee that 2 students would have the same score on this exam. Everybody got why I had to choose 102 as a number here for the example? What happens wrong if you had 101 students? Well, every score could have been represented once and only once. So if you count the integers from 0 to 100, including 0, including 100, there's a total of 101 of them, right? Just quick follow-up though, idea, like is it possible with 30 students? If you have a class with 30 students, is it possible amongst 30 students to have two or more students with the same score? Well, yeah, sure, it's certainly possible, right? You could have this class of 30 students. They could have all gotten hundreds. That everybody got a perfect score. That's possible. It's possible, right? It's possible for in a class of 30 for multiple students to have the same score. But when you have 30 students, it's also possible that they just all had literally different scores, right? So the point is this guarantee of the pigeonhole principle. You've got to have this imbalance situation. It's got to go the right way. Of like, you see here that in this setup, what are the pigeons and what are the pigeonholes, right? So, like in this example with the 300 students, the I don't mean to be demeaning, but like this is kind of often the way people will argue things of like the 300 students are the 300 pigeons, and then the 101 possible test scores are the 101 pigeonholes. Right, just to make sure, we'll try another. Like, kind of bring things back to, let's say you have two sets A and B. Cardinality of A is bigger than cardinality of B. Then there are no one-to-one functions from A to B. Right, there are no injective functions with A as the domain and B as the codomain if the cardinality of A is bigger than the cardinality of B. And think about what's going on here, right? The idea that there are no one-to-one functions. Think about what the pigeons are. What are the pigeons here? What are the pigeonholes? Right? So what are the pigeons here in this setup of the pigeons? That's the thing there's more of, right? And I think sometimes an answer that people want to give to this is, oh, the pigeons, that's A. Well, let's just to be clear, since it is pigeons plural here, let's just say that the pigeons are the elements of A. And then the pigeonholes are the elements of B. And it really works with what's going on with a function. It's sort of like each pigeon choosing which hole that they fly into. That's like what f of that specific pigeon is, right? Like there's this sort of a good analogy between functions, like the output of a function. Each domain thingy has one thing in the codomain, right? That's called the output. It's like each pigeon choosing which hole that the pigeon flies into. There's a formal statement of the pigeonhole principle. I wouldn't stress about this too much. I mean, I just need to state it once, perhaps. The formal pigeonhole principle makes it sound like these are pigeons that are wearing bow ties or something. Makes no sense. So let A and B be finite sets satisfying the cardinality of A is bigger than the cardinality of B. If it's just sort of a contrapositive version of the example we just had, actually. If f is a function from a to b, then f is not injective. That's it. There are functions from a to b, but if the cardinality of the domain is bigger than the cardinality of the codomain, you can't have an injective function. So this is the formal version. It's the one that sometimes books present this and then this formal one first, and then bring up the actual pigeons and the cubbies next. But I think I wouldn't think about it this way. To be, it's formal. It connects to the things we've done, but it's excuse me. This is, I think, a topic where it's totally fine to just think about it the informal way with the pigeons and the pigeonholes. Okay. There is a generalized pigeonhole principle. And this also, we don't prove this statement, but it should be true, right? So it goes like, here's a way to state it. So if capital N, if you have n pigeons, and if these n pigeons fly into, so there's a total of k holes, so k pigeonholes, then there must be a container. But container, I just mean the same as the pigeonholes, right? So there must be a container with at least fraction n over k, and then I'm going to apply the ceiling function. I believe we talked about that ceiling function recently-ish. Pigeons. So take the number of pigeons, divide by the number of pigeonholes. So that already, without the ceiling function being applied, n over k tells you, at least roughly, the number of pigeons per pigeonhole. And then if you just told all these pigeons, you each got to pick a pigeonhole, then there's got to be a pigeonhole that has more than the average number of pigeons per hole. That just has to happen. So let's look at a silly example of this. Okay, let's assume that nobody has more than 400,000 hairs on their head. So, it's an assumption, but let's go with it, and it'll make the argument here work. So I mean, count like the integer number of strands of hair that somebody has on their head, right? Like, it will never exceed 400,000. We'll just say, since Chicago has a population of 2.7 million people, there must be, at least 7 people. There must be 7 people, maybe even more, but there must be 7 people in Chicago with exactly the same number of strands of hair. On their heads. So all that's going on here is, how is this an application of this principle? It's just, you go into a Google search and you do whoops, that's 2,700. That's 2.7 million. Divide by 400, comma 000. 6.75, right? But that's not a whole number, and this function over here, the ceiling, just grows this 6.75, right? In this example, n over k is 6.75. So then when you apply this ceiling thing, it just keeps growing the number until boom, you hit an integer. So this is 7. So if this assumption is correct, that nobody could have more than 400,000 hairs on their head, and by number of hairs we're always just counting, the result is going to be an integer. There have to be at least 7 people in Chicago that have exactly the same number of hairs on their head. Try this. The UWL student population is approximately 10,000 students. So there are at least, again, you can always insert the phrase at least. There are at least ceiling of 10,000 over 12. There are at least 10,000 over 12, round up until you get an integer, students with the same birth month. Yeah, 12 possible months, 12 possible birth months. Hope we're doing okay, right? So again, the pigeonhole principle is just to argue there's more of this than that, is all the pigeonhole principle is really about. And the generalized pigeonhole principle is to help quantify that a little bit, right? It's like that there's this many students that need to share being born in the same month at UWL, right? So I want to end on the following question. I'll say that the proof we're about to look at is a little bizarre. I'm not expecting you to recreate this argument necessarily. I just want you to follow it. So don't stress about it too much. Feel free to ask questions. And it's a little strange, but it's just sometimes the questions, in order to apply the pigeonhole or generalized pigeonhole principle in settings, they're sometimes somewhat strange questions. So let's go for it and see what happens. I don't want you to stress out over this particular proof or this argument by too much. Not from a standpoint of you won't be recreating it, you won't have to prove something quite as involved, but let's just talk through it. So assume that 6 people, and it will be convenient for me to name them using the last 6 letters of the alphabet. U, V, W, X, Y, Z. Those are their names. Okay, these 6 people, among these 6 people, I forgot a word here. Assume that among 6 people, each pair of individuals consists of 2 friends or 2 enemies. So the 6 people, so what I'm trying to say is among these 6 people, they all know each other. It doesn't always happen in life. You can pick 6 people at random, and there are people like, I don't know that person, right? But like in this case, not only do they know each other, there's this built-in assumption in the problem that you pick 2 of the people, and they're either friends or they're enemies. So first of all, the total number of relationships here, 6 choose 2, right? So in each combo of picking 2 people, either those 2 people like each other or they hate each other. They're friends or they're enemies. It's simplistic. It's not realistic. They're people who just, whatever. We're going with this just to argue something here. And what we're going to do, the task is to show that there are either 3 mutual friends or 3 mutual enemies. So among these 6 people, I'd like to provide an argument for you to show that either 3 of the people, mutual friends, meaning like there's 3 people, maybe it's U, V, and W. I don't know which it is, but maybe U, V, W, meaning like U's friends with V, U's friends with W, V's friends with W. All 3 of those people, they're all friends with each other. All 3 of them would hang out with each other. Or 3 people that are mutual enemies. So I'd like to argue that out of this group of 6 people, a subgroup of 3 people where they're all either all friends or all enemies that has to exist. So to answer this question, I'd like to just consider and just fix one of the people. Consider person U, just the first person here, right? Person U, just one of comma, and just for clarification, one of the 6 individuals. I just picked one of them at random, and why not just the first person, just to make this easier. Now, what I'd like to do is distribute the remaining 5 people. Distribute the remaining people into 2 sets. Those 2 sets will be called capital F and capital E by the following rule. So here's the rule. Friends of person U are placed in F. Enemies of U are placed in E. So capital E and capital F are sets. Every person other than person U, so these other people, V, W, X, Y, Z, those people, each person will either end up in set E or in set F, depending on whether they are friends with you or not, or friends with you or enemies with you. So what we have here is since each person is either a friend of you or is an enemy of you, and there's no in between in this right now. So so that means here that F and E are disjoint. There isn't an individual that's both friends and enemies with you. It's one or the other. And since everybody ends up, all of these 5 people from V onward to Z end up in one set or the other. We have this disjointness. There's these 5 people in total between the number of people in F and the number of people in E. These 5 people end up in either set F or set E. So what are the pigeons? What are the pigeonholes here? Let's pause for a moment. What are the pigeons? What are the pigeonholes? What do y'all think? Okay, F and E are the okay, so F and E are the 2 pigeonholes. Yeah, the 2 sets. And the pigeons are the 5 people. Right? So 5 people, 2 pigeonholes, right? Like these 5 people, there's like 2 boxes, right? Or 2 doors, and so if you're friends with person U, you go through one door, and if you're enemies with person U, you go through another door. So there must be ceiling, not 6/2, because I know there's 6 people total, but person U is left out of being placed into one of the sets F or E. So there must be ceiling 5/2 in one set, right? So just so I can write this, so it's here. The 5 pigeons are person, let's say after U, so U, V, W, X, Y, Z. And then the holes, the two pigeonholes, the two pigeonholes are the two sets F and E. Right? So by the generalized pigeonhole principle, by the generalized pigeonhole principle, um, one of at least one of F or E must have cardinality at least five choose two ceiling of five choose two. And so 2.5, but when you ceiling, you keep raising that number until you hit an integer, so you'll get up to 3. So either F has cardinality 3, right, or E has cardinality 3. Ooh, I said or. You know what's coming up. We heard an or. Case 1. Case 1. Suppose F has cardinality at least 3. So suppose F has at least 3 people. Now, F could have more than 3 people, but we'll just go with F has 3 people. At least 3 people. Right? And then case 2 will be down. I'll just write the case down here, and we'll come back to it. So since either F or E has to have at least 3 people, those are the two cases. One of those things has to happen. So either F has at least 3 people or E has at least 3 people. So I left some space because I want to actually I want to fill in this part first, and then we'll come back to case 2. All right, so we're in the situation right now of suppose F has at least 3 people. Let's just there might be more than 3 elements of F. Okay, but we only need to work with 3 of them. I mean, the worst case scenario, there's only 3 things in F. So to name these 3 people, I'm just going to say that suppose they were. I'll just use the letters after U. So V, W, and X. Now it might not actually be those 3 people, right? It might have been 3 other people, but it does. I mean, the whole point is like, let's just rename them, shuffle them around. Like, if it wasn't V that should belong to this set, maybe it was Z that should have belonged to this set. We'll just have V and Z change names. That's all, right? Swap names. So we'll just say that these 3, because at this point it doesn't matter which 3. It's kind of an arbitrary thing, right? Of which ones are elements of capital F. And so just to restate what's going on, if V belongs to capital F, then we're saying that U is friends with V, and U is friends with W, and U is friends with X. That was the definition of capital F. Capital F had those people that were friends with capital U. Now, here's the thing. If any 2, we're really kind of breaking the subcases, but without so much formal language because we're so close to done here, okay? If any 2 out of these people, V, W, and X, are friends, there are 3 people here, V, W, X. If any 2 of them are friends with each other, so you just ask V, W, and X, like, hey, V, W, are you 2 friends with each other? Yes or no? Hey, W and X, are you 2 friends with each other? Yes or no? So if any 2 of these out of these 3 are friends, then those 2 and U form 3 mutual friends. right? So out of these three people, you just ask amongst these three people, like they're sort of standing in a circle or a triangle, I guess. There's three of them. You just ask amongst these three people, would any two of you hang out with each other? And if two of them would, maybe it's V and X that would hang out with each other. If they're the friends, then V and X are friends. And remember, all three of these are friends with capital U. So, I mean, there's sort of so many subcases. It's not worth actually enumerating all the subcases. It's just if two out of these three people between V, W, and X are friends, the two people who are friends here were also friends with U. Remember, but that this if thing might not happen. So the negation of any two of them are friends is as follows. So otherwise, if out of these three people, none of the V and how would this be false? Any two are friends. It'd be that all three of those people are not friends with each other. Otherwise, V, W, and X are all enemies of each other. And that's fine too. Remember, in the beginning of the statement of this theorem, we needed to prove that there were either three people that were mutual friends or three people that are mutual enemies. So these are all enemies of each other. So, excuse me, V, W, and X are three mutual enemies. How are we doing? Because this finishes case one. Case two is extremely similar, actually. We'll just kind of wait here for a little longer. Just make sure we're as okay as possible with this argument. It's sort of a little, technically sort of that text here versus the other text here. So the two pieces that are in blue, the two blocks are sort of subcases to case one. But since they're short, they were just kind of each written in a sentence. So in case 1A, you have three mutual friends. In case 1B, we produce three mutual enemies. Any takers on questions? Okay, case two. So remember at the top we had the two pigeonholes, which were E and F. They, at least one of those sets had to have cardinality at least 3. So it was either the set F had cardinality as 3, or set F had cardinality at least 3, set E had cardinality at least 3. Now we're looking at the set E has cardinality at least 3 situation. And so there's these at least 3 people in capital E, and just again to name them, say that it's V, W, and X are the 3 elements of capital E. You might be bothered that V, W, and X were over here elements of F, but we're in a new case. It's its own separate independent paragraph. So this means that U is enemies with V. That's what it means to belong to capital E. Remember, E was defined as those people that are enemies with U. So U's enemies with V, and U is enemies with W, and U is enemies with X. So then the text that we're going to write now looks very similar to the block that's still kind of up there outlined in blue. So if amongst V, W, and X, amongst these 3 people, if any 2 are enemies, then those 2 together with U form 3 mutual enemies. So you got these three people, V, W, and X is what we're saying their names are right now, and you ask amongst those three people, hey, can you point to some out of these? These three people are standing around in a circle. Point to somebody whose guts you hate, and say, two, at least two people point towards each other or something. Then those two people that don't like each other, they also don't like you, right? So the all three of those people form three mutual enemies. Otherwise, if this condition doesn't happen, if amongst these three people, V, W, and X, we don't have this situation of any two enemies, it's because those three people, V, W, and X, remember it's one or the other. Like any two people in this situation either need to be friends or enemies. Otherwise, what's going on here is that V, W, X, those three people, form three mutual friends, or three mutual friends. So again, here are the general ideas. We've got like a case 2A that I'm kind of highlighting in red right now. And then in the other portion of this paragraph, and partitioned off, this is sort of case 2B if you wanted to like really break it down and make it much more formal. In both cases, each case 1, case 2, each broke into subcases, and in each subcase produced for you either three mutual friends or three mutual enemies. So that does actually conclude the proof. Sort of a little bizarre proof that applies the generalized pigeonhole principle. Zoom out a little bit, see if we're doing okay. Ask questions. Again, just in terms of announcements, a quiz, Wednesday's response, and what we'll do tomorrow and Thursday. No more new content. We're done with new content. All I want to do is design some practice problems tonight, and we'll just practice some proofs. Things that were probably more challenging though, right? Like functions stuff, some set notation business, and just nothing new. I mean, I would still come to class tomorrow or watch the video or whatever, but like no new things, no new definitions, nothing like that, right? We're just gonna practice for 2 days. We good? Just ending early, but just sticking around in case there were questions about